Hey everyone, welcome to my YouTube channel. Today we will understand the pumping lemma and try to use it in a question to show that a language is not a regular language. First of all, let's try to understand what pumping lemma says. We know that all regular languages can be expressed using finite statements or regular expressions. And we know all regular languages will share the same properties, such as the closure properties, which state that the regular operations like union, concatenation, and the clean star of regular languages are also regular. Pumping lemma is another property of regular languages. We use pumping lemma as a way to prove that some languages are not regular. But didn't we say that we can draw a regular language finite statement? But think about a scenario in which the language is not regular and you have to prove that it is a non-regular language. In that case, since it is not a regular language, you can't draw any finite statement. However, being not able to draw a finite statement does not mean that this language is not regular. In order to prove a language is not regular, you have to use pumping lemma. As we said before, each regular language should satisfy pumping lemma. In order to satisfy pumping lemma, you should satisfy the following properties. The first property says that for any string, there will be a part that can be pumped any number of times. Pumped means repeated any number of times, which we call y. The second property says that we cannot pump the empty string. So the length of y should be greater than 0. And the final property says that its length must at most p. We will look at that later in our examples. So that means as long as a language is regular, then every string in the language will be able to meet these three conditions. If it doesn't meet any of them, then we can clearly say that that language is not regular. So all of these three properties state that if a language is regular, then every string in the language will have a section that can be repeated or pumped any number of times and still be in the language. Let's look at it with an example to understand it better. Let's say we want to prove that B is not a regular language. In order to be in that language, the number of ones and the number of zeros should be equal, and any string which belongs to that language should include first ones and then zeros in that order. And the number of ones and the number of zeros should be equal. We can't draw any finite statement, but it alone doesn't mean that your language is not regular, okay? That's where the pumping lemma comes in. Let's prove that B is not regular. In order to do that, we should follow a guideline. First, we will do that with a contradiction. That means we will try to prove that it is a regular language, although we know it is not. Then, since it does not satisfy the pumping lemma, the properties of pumping lemma, we will say that this language is not a regular language because it doesn't satisfy the properties, the requirements of pumping lemma. So first, we assume B is a regular language. And if B is a regular language, then it should satisfy the pumping lemma because pumping lemma is a property of a regular language. First of all, we need to find different cases in which we can choose different y. We can choose y from the middle of the language or from the left side of the language or from the right side of the language. So we should find each cases. For the first case, we will take y from the left side of the language. So our language is 1, 0. Let's assume that p is some integer. If we take y from the left side of the language, if we say this is y, then this means that in order to satisfy the pumping lemma, if we repeat y multiple times, if it is a regular language, it should be still in the language itself. So the resulting string should be still in the language. But in that case, this string, which will result something like that, 1 1 1 1 1, and then 0. Right? Let's say we repeat y 2 times. Is it still in the language? No, right? Because the number of ones are higher than the number of zeros. So it is not in the language according to the language definition. Let's look the second case. Again, we write our language, and let's pick y from the right side of the language. Let's say y is here. In that case, let's say we will repeat y 2 times again, let's say. Again, since the number of zeros are higher than the number of ones, this string does not belong to our language. First case is failed. Second case is failed. Let's look the third case. Let's pick y as the whole pattern, okay? Let's say this is the y. Let's repeat y. Let's repeat it several times. And it continues like that, let's say. Does this string belong to our language? No, right? According to our language, this should be like that. So we can clearly say that. Third case is also failed. Therefore, this string cannot actually be pumped. And as long as there is one string that is at least length p that cannot be pumped, then a language does not satisfy pumping lemma. And therefore, it is not regular. And that's all. I think it's easy, and we can use it whenever we are trying to prove that a language is not a regular language. Since the language is not regular, you can't use the finite state mention, because you can't draw any finite state mention which recognize that language. In order to prove this language is not a regular language, you should use pumping lemma. And this is all for today's lecture. In the next lecture, we will explain the halting problem. I hope that you have enjoyed watching this video. See you in the next lecture.